respected and overwhelmingly forward for. The number of participants has increased. It's partly, I believe, because of the AI assistive writing and AI assistive research also accelerated in the domain, the number of publications and the speed at which we publish as well. So it's not purely, I wouldn't take the whole credit to ourselves, but at the same time, we also see like there's a huge interest from the students community to industry to be part of this work. Like, so we had about 200, submissions at least, active submissions, like, and then from there, we were able to cut down to 50 main papers, I believe. So that's the current status we have. We have differentiated like both undergraduate and postgraduate separately for the benefit of the review as well as for the benefit of the audience. Further to that, we kind of nicely balance the practical application as well as the connection to the AI and data science theories. So we're not completely thrown off the core ideas or fundamentals. So today, I encourage all the participants to make full use of this opportunity. The main reason we come for physical conferences, especially with the current, situation in Sri Lanka, is very hard to afford an international conference, go and meet people. We have come a long way going back into these virtual pockets during the COVID. We have come a long way to come and physically meet. It adds a lot of value when you meet a person, listen to somebody's ideas, somebody's presentation, somebody's research work, what they do, what is happening. So it will be a huge accelerated learning curve. So make sure that you not only focus on your work, try to connect, network with people, get to know not only your peers, even the, some of the accumulated researchers who are here as reviewers as well as judges for the event. So please do connect with everybody. The interactions often lead to collaboration, so it's very important for all of you to keeping that in mind, especially in the current phase of the industry and the slowness in the industry. Networking could play a long way for you. Once again, my sincere thanks to everybody, and have a great conference ahead, and all the best. There are some great awards aligned, so hope you impress the judges and all of you take something from today. Thank you so much.
Thank you for those insightful words, sir.
We now move into one of the highlights of ADScAI 2026, the presentations of best papers across all tracks. These presentations showcase some of the most innovative and impactful research contributions in areas such as applied AI, data systems, and real-world AI applications. Please note that the allocated time for the presentation will be 10 minutes, followed by a 5-minute Q&A session. The speaker will be first indicated at the end of 8 minutes and again at 10 minutes when the time elapses.
To start the set of presentations, we invite Mr. Pasindu Givinda to present his paper titled Real-Time Environment Adaptation Using Telemetry-Driven Behavioral Clustering and Neuro-Fuzzy Procedural Content Adaptation.
Hello, I am Pasindu Givinda, and this is my research project. Actually, basically what happens here is, so when the game player playing in the game, so when a player try to play a game, there is some like skill-based adaptation, but when it comes to a player, that would be unfair to him. So this research focused on that. So my solution was architecture. So Aura architecture means adaptive user responsive architecture. So let's how so so if we talk about why existing system fails, so first of all, there is a quality start bias. So when a player try to start a game, the adaptation system try to adapt to the system from the player's first skills. But when it comes to start the gameplay, the player don't know about anything of the game. So there should be a time to adapt for him, and so the baseline should be fixed before the game is start. So that was one problem. And as the second problem, when developers try to implement a model for the game, so they are facing an issue, the black box issue. So they can't know what happens inside the ML model. So they want to know how the decisions happen, otherwise they also would be confused and they can't optimize the game as well. So the third one is agency violation. So agency violation means so agency violation means, so let's say a player is playing and the model adaptation the environment. So when the environment adapt, let's say we have enemy and player attacks to the enemy, and system identified him as an attacker, and the combat skill also goes high, so enemy difficulty suddenly goes up. So that can't be happen. That's also a problem in the system, current systems. So the gap. Previous one. Okay. So we have three gaps here. So we have to go through two phases. Like we have to separate the calibration phase first, so the user won't get confused and quality start bias can be misplaced. And so when like that in my design, my game design, we have three archetypes: combat, explorer, collector. But in that, in that situation, when a player try to cluster the player's telemetry, there can be hard clustering. So first time system can identify the player as combat, then explorer. So environment can shift suddenly, so hard clustering is not the solution. So that's also a gap. So my system try to avoid that too. So reactive. So reactive means likewise I said, when user attack, enemy difficulty go high. So that also a gap. We have to solve that too. So in my system, so as I said, calibration first. In the phase one, we gathered some telemetry and process, and we set the default neutral baseline. So after that, we can avoid the quality start bias. And soft membership, I'll explain it in after slide. So forward only, also the forward, as I said, sudden changes. When a player attacks, enemy difficulty goes high. So that means in the environment, current environment, we can't change anything happens. We can only change what happens afterward in the next regeneration. So that's my focus in this system. So let's move into the next slide. So here is the high-level architecture diagrams of my system. So in there, first as you can see here, in this paper, I only defined two phases. Actually, there is a three phases, and I have identified it as a future work as well. So in the phase one, actually, what I done is, so I randomly chose 7 participants and give them a 3 mod-based game, so prototype game, and let them play. Actually, in that gameplay happens, I didn't adapt anything in the environment. So it was a fixed environment, so nothing happens. So the player plays, and randomly also game mode changes. They don't know whether what is hard, what is easy, what is neutral. So based on the gameplay, I chose the actual neutral baseline. So using that baseline, I fixed those parameters in second phase, and also I distributed to 47 participants, and the game also I let them play it for 40 seconds, and they also don't know the game. So in the second phase, what I want to do is collect the telemetry data to implement my model. So for that, actually, I had to fix the adaptation environment, and also the cold start bias. As I said, when a player starts the game, they don't know about the system, they want some time to learn. So there will be noise in the dataset if I use first 20 seconds. So after 20 seconds, from 22 to 40 seconds, I got all the data and use that data to process. And after the model implementation, what happens is this diagram. So there is Unreal Engine in first left side. In the Unreal Engine, no, that's right, previous slide. So in the Unreal Engine, actually, we collect the telemetry data. This is after the implementation, actually, phase 2, phase after. So dataset collect for 30 seconds windows, and using that 30-second windows, we send to backend inference, backend deployed inference setup. So after processing in multiple backend processes, we got a target multiplier. Actually, that is the variable I'm going to change my environment's difficulty. If the player is playing too hard, we want him to play, get the playing game, get to difficult game, increase the difficulty as well. So for that, I use that variable. So send that to Unreal Engine, and using that, I don't immediately change the environment. I just change the environment in the next generation. Actually, I used the PCG in Unreal Engine build framework for that. Yeah, so yeah. So calibration first design, as I said, I used 7 participants and got their data for 3 modes, and randomly they chose the mode as well. So in there, actually, this is my defined formula. So neutral ISCO, actually, it used the formal theory. Yeah. So in there, what happened is, so we have to, in the game for player satisfaction, we have to ensure the player played 85% satisfaction level. So to calculate that, I use this formula. So what happens in there? So balance activity. Balance activity means we have to know they played in every archetypes, compact, explorer, collector. In that, all archetypes should be there. And signal stability. So if all the, like guys, when let's say we are collecting for attacker, parameters are, so how many kills he got, how many attacks he done, like that. So if that all doesn't have happened in the one session in 30-second telemetry window, so if that doesn't happen, so signal stability also goes high. So safe challenge. So safe challenge means death rate actually. If the player died multiple times, he will get frustrated of the game. So he will abandon the game because of the boredom. So neutral score, actually there is a weight as well for each of these. I gave my own weights for that. Actually death rate got the highest weight. So death rate was safe challenge. So likewise, I used this calibration phase to choose the best mode. Actually, mode 1 was the best mode because it was the lowest neutrality score had. So based on that, I used that one. So yeah, soft behavior clustering. So after the first phase, I got the mod 1 as the baseline neutral parameters. I don't want to change that in phase 2 because I'm going to collect the data from users to implement the model. So for that, actually, I use soft behavior clustering after that data collected. As I said, I used only from 20 minutes to 40 minutes only to avoid the data noise. So using soft behavior clustering, what happened was, actually in my game, I collect for combat, there was 5 parameters. For explorer, there was 4 parameters, and collector, there was 2 parameters. No, three parameters. So using those parameters, actually, there will be unbiased when we given the percentage we are clustering because there are multiple parameters. So we had to get mean for each archetypes. Using that each archetype's activity score percentage that got by mean, I used to cluster. Actually, there was one way also. Actually, I got the sum, and we got the sum, and we divided it by all of the collected sum of all. So based on that, I got each of the archetypes percentages, and using that, actually, I trained the k-means model and got the centroids, and based on that k-means centroids, I used each of, for k-means centroids, I calculated for, in a prediction, I calculated from that predicted data points to each of the archetypes distances. Based on that, actually, I done this clustering and explainable adaptive inference. So that clustering part was another one. So actually, for the clustering, for what games happen is every 30 seconds in the game, they send a telemetry. After 30 seconds, the game sends a telemetry data to the backend. So first process was to clustering, then this one. No, previous. Yeah. So the explainable adaptive inference. Next one. Explainable adaptive inference. Actually, in my system, functionality requirement was to have the prediction within 1 millisecond, below 1 millisecond. So for that, actually, I can't use that ANFIS. Actually, there was I can't remember the research paper. There was a theory for fuzzy rules. Actually, we can use that to made a formula and use that inside the game, but I can't do that because otherwise it will take time to process and it will be 50 to 200 milliseconds. So what I do is, as I said, I defined the adaptive multiplier target, so variable. So after that, I for using that formula, I created data set again, another column, so adaptive inference values. So use that, actually I trained a MLP surrogate model, So using that neural network model, actually we can achieve the 1 millisecond, within 1 millisecond response. So that's why I used the MLP surrogate, and otherwise I can't use that Gaussian fuzzy rules. We can actually black box model also, the issue black box model issue is in neural network, this neural network MLP surrogate model. But we can avoid that. Actually, developer can understand what happens using the ANFIS in offline process. So using that, actually we defined a variable and use that variable, we trained a model, and we only use that model, trained model in the system, and we can integrate into our Unreal Engine environment and use that. So next slide. So as you can see here, so after I trained the MLP surrogate, so there was ADScAI value was that turns ADScAI value was 0.9264. The distribution of the data set you can see in here in the diagram, distribution of the target multiplier that I said the variable I used to train. So, and also after the soft cluster membership, soft clustering, you can see actually the data set also explicitly distributed across all archetypes, as you can see in here second diagram below. So the results was actually behavioral validity also achieved, and adaptive stability, and bounded output means actually let's say the target multiplier distribution as you can see in here, but there will be some cases the user played out of the system, like there will be some player who has skill more than the normal user. So, but the system can't be handled that much. So PCG can't handle some outputs. The game will stuck, something will happen. Game will corrupt in the time. So for that, I had to bound the target multiplier in that case by going through some test cases as well. So bounded output was, as you can see here, 0.6 and 6 to 1.4. So, and so as I said, I had to I can't create an NFIS model because it will take 200 to 50 to 200 milliseconds to run. So I had to use MLP surrogate model. So it gave me 92% accuracy, but it was a test data set I used in the process. So I had to do multiple mixes and had to check whether the model is accuracy for all of the time. So the output was, as you can see here, 0.8 to 0.995. Yeah. So 95% time it was correct. So next slide, please. Yeah. So calibration first. Yeah. As I said, there was a cold start issue when a player start a game. There will be some cases the player had to play the game without knowing the game, but game is going to adapt. But I avoid that using calibration first design. And so we can't say a player is an attacker, a explorer, a collector. We can't say that exactly the person is going to be that archetype. Otherwise, it will be very unfair. So we avoid that using soft membership. And hard clustering issue, as I said, when player plays, sometimes system suggest as he is attacker, but next time going to be an explorer. The environment will be shifting. Suddenly, the player also will get confused. That also avoid using soft membership clustering. And explainability and milliseconds achievement also happen using neurofuzzy surrogate model. So forward, yeah, forward only adaptation means, as I said, the game only going to adapt in the next generation. So there will be no player agency preservation as well. So as I said, that won't be not unfair to player and he won't get confused. So that's all. Yeah. 8 seconds. Yeah. Okay. So if there is any question, mic is yours.
What's the meaning of accuracy in this context? It was not clear. You have an accuracy figure.
So I can't hear clearly.
Here you have quoted an accuracy figure.
Yeah.
What does accuracy mean in this context?
Yeah. So actually, I did evaluation only in the system. Actually, this paper only focus on the architecture. So I currently doing on the PCG integration and the user evaluation. Haven't done qualitative evaluation, but for the can I? So
But you have a figure asked an
what's
You have a figure there asked is 92.
yes.
What's that?
Yeah. So R2 square means, as I said, I implement the MLP surrogate model. So that model going to identify how the so as I previously said, we can use fuzzy logics. Actually, we had to perform create a formula for our own game. It would be adapted only to our game, and using that, I generated that target multiplier. And so using supervised learning, I am going to train them. I trained the model MLP surrogate. So that MLP surrogate model had that 0.92.
You also talked about this clustering, soft clustering, but you mentioned centroid model.
Yes.
Normally, most centroid-based clusterings are partitionable. How do you get soft clustering from?
Yeah. So actually, sir, we had 3 archetypes. So for each archetype, actually we using the Silhouette score. Actually, it's depend on the game. My game also biased to 3 clustering. So it gave me 3 clusters. So based on that, actually that 3 clusters, we have 3 centroids. So soft cluster, I collected the telemetry data. So using those archetypes parameters, I got the mean values and sum of all mean values together and divided for each, and I got activity score for each archetype. So after that, I trained the model using that activity score percentage. Activity score percentage is the used to train, and using that actually, when predicting actually what happened was, soft clustering happened was, so using that got activity score, we are going to get the distance from that each archetypes to according archetypes centroids distance, and we divided it using the distance divided from 1, so we can get the distance, and they are also going to be a sum. They are also going to sum together and divide and get the soft percentages. phase 1 motivation.
The motivation of facing a weight cancer and how did you select the weight?
So actually in the system, so phase 1 or going to identify the system's baseline model. So using that baseline model, actually that would be fair for all players because we got the values which will best suited for the beginner. So that identified, as I said, for the second time when I used to collect data, I had to cut from until 20 minutes because that noise data the player don't know about the game. But when I divide him first phase to the players to play, they don't know also about the game, and I only let them play 7 seconds in each mode. So there will be that noise as well. That noise is the beginner's noise. So I identified through that and using that mode as the baseline, and I used the baseline mode for the second phase starting point.
My question was around the weighting cancer that you
Ah.
mentioned during the calibration phase.
Yeah. So neutrality score 1, right? Neutral.
Weighting cancer. You mentioned about weighting.
Yeah.
Yes, I think you talked about the weighting.
Yeah, mode selection weightings. Yeah. So neutrality score, that was a formula based on formal theory. So we had to focus on 85% accuracy of the model. So not the model player satisfaction. So 85% satisfaction. For that, actually, when a player play the game, if he died multiple times in that mode, actually there doesn't mean using that mode because he will get boredom and frustration. So for that, actually, I had to move my weights as I want. Actually, that depends on the game. This is a architecture, so depends on how the game will design. So in my mode, actually, death means frustration. So I had to increase the weight of that death rate. So like that, I handle others too.
But so for community, you have used time this right?
Yeah.
5 minutes. So have you checked whether the size of the time will affect the overall performance?
So you are asking telemetry window sizes, right? Yeah. So actually, let's say in my game, so 10.
Have you checked whether there is some kind of relationship between the window size and the performance of the
Yes. Yes. Actually, let's say 10 seconds. So the environment going to change after 10 seconds based on the previous 10 seconds. Next 10 seconds depends on the previous 10 seconds. So the player don't even had to do anything within the 10 seconds, and that's depend on also the parameter. So parameters are going to be some that like very small ones, so they are doesn't mean so. But if the telemetry window is high, let's say 60 seconds, the previous 60 second player's intention was to kill enemies, but he got bored. But so he used to explore. He's trying to explore, but enemies are going to spawn in next 60 seconds. So that's the issue. So 30 seconds was the best.
In 2008, they had something called the AI director, which tests what you are doing, taking in telemetry and making the counts and the difficulty of an execution are easier and so on and so forth. So I wonder whether you look at it in a study and what is if you have, what is the difference in your system versus AI?
Yeah. So actually in my system happening, so I used to collect how they explore and how they attack to enemies, how constantly attack, how constantly he was uh, in the FK or like that. So based on that, actually in my game there will be going to spawn enemies. There was a enemies cap 2. There will be going to spawn enemies, and also enemies difficulty going to be changed, and count of collectibles spawns also going to be changed, and all of that I set using a PCG, procedure content generation. Actually I already implemented that part as well, procedure content generation, and those parameters are going to change based on target multiplier. As I said, I had to bound the target multiplier within 0.6 to 1.4, because otherwise if that increase, that PCG going to be messed up. So that also design decision. For my system, I can't increase more than that and less than 0.6. So that based on designer.
Whether you have a knowledge beyond what we are doing as well. So you are saying the difference is that they are only concerned about enemies and they are looking at the loot as well.
Yeah, so it's based on the game designers. Actually, my game, my focus only for that. Actually, the archetypes designed by designed by me. So combat, explorer, character, but there will be more than that. And based on the design, based on the game design, the output also can be different. I use procedural content generation to spawn enemies, spawn collectibles, and I couldn't handle in my PC. Actually, if I can, I could be implement to explore new caves like that for explorers, like that.
Okay.
Okay, so that's it. Are there any questions? Okay, thank you. Thank you very much.
Thank you, Mr. Pasindu. Kindly note, the speaker will be first indicated with one bell sound at the end of 10 minutes and two bell sounds at the end of 12 minutes. Next, we invite Mr. WMTN Vijayakon to present his paper titled A Modular Spatio-Temporal Graph Neural Network Framework for Multi-Step Forecasting on Graph-Structured Data.
Hi, good morning everyone. I'm Taranju Chekon and I'm here to present our work, Modular Spatio-Temporal Graph Neural Network Framework for Multi-Step Forecasting on Graph-Structured Data. So our work, we focus on improving the way how we train and evaluate and also reproduce spatio-temporal graph neural networks. So let's move on. So first of all, spatio-temporal graph neural networks are very crucial in various applications, especially like traffic forecasting and also epidemiology forecasting, and also any kind of sensor network that has both temporal and spatial information that can be encoded into the model. And that's actually the challenge of using spatial temporal graph neural networks, because we have to encode both spatial aspects as well as the temporal aspects. So even though there are a lot of STGNN models, or in short for spatial temporal graph neural network models, everyone has different every model has different architectures, different implementation, and we were back then doing research using these STGNN models, and we came up with a problem that every model has different architectures and different implementation and different ways to input data, and it was really hard for us to actually implement various models and like try those models in our application. So we came up with a solution for that. We created a modular framework where regardless of the architecture of the model, or regardless of the implementation of the model, we can input the model into our framework, and like we made a standardized framework. So like some of the key issues that we identified in most of the existing STGN implementations are lack of modularity, difficulty in reproducing results, and also they don't really have a standardized way to compare models across datasets. So what is a spatio-temporal graph neural network? So basically, in most of the machine learning models like ARIMA or LSTM or GRU, we usually only have the temporal aspects. Then we have the graph neural networks that input the spatial relationships into the play. So spatio-temporal graph neural networks is a combination of both. They have both the temporal aspects as well as the spatial aspects encoded into the model, so we can integrate both of those aspects when we are forecasting or predicting or actually utilizing our model. Yeah, so in this work, what we are contributing is to create a modular STGNN framework, so we can integrate different models into a same framework and get the forecasting jobs done. And also we are integrating MLflow to create reproducible pipelines, so we can reproducible pipelines, and also multimodal support. And so our output of our framework is a multi-step forecast. So integrating MLflow into our framework helps us to have consistent training, evaluation, and also validation across different models, different domains, and also different datasets. So this is a very high-level diagram of our framework. So as you can see here, there are some key components here. First of all, I think like one of the most important one is our data module. So this is where we actually do our whole data pre-processing workflow. So everything from processing the data, feature encoding, to selecting sliding windows, scaling, everything is done in this module. Then we have the most important part, the GNN module, or graph neural network module. So this is kind of like the highlight of our framework. So this is where we have implemented that modular structure. So we are using PyTorch here. So regardless of the actual model architecture, usually spatio-temporal graph neural network models have two different components. So first one is the spatial component, and then we have the temporal component. So here in our GNN module, we are mainly using graph convolution networks to create the spatial part of the model, and to the temporal part, we usually use sequencing. Sometimes like we have attention mechanisms attached here as well. But yeah. Then also we have the training module. So this is where the whole training part is done. All the hyperparameters and also optimizers and everything related to training is done in the training module. Then model store stores the trained model, and in the inference and evaluation module, we use the trained models to for the inferencing and also evaluation, and also like get all the visualizations Yeah, basically we use inference and evaluation model to test our models. So we use ML flow here so we can track our experiments. So yeah, what did I mean from modular GNN design? So in our case, like as I mentioned before, like each spatiotemporal graph neural network model has different architectures, and also they have different implementations. So we are creating an interface where we can plug almost any STGNN model and give it a input as the historical data and a adjacency graph, and it will output what we need, like multi-step forecast. And it doesn't depend on the actual implementation of the model. We can basically input any spatiotemporal graph neural network model and get our work done from this one. So for the research paper, like we did some experimentations with 2 data sets. We used the LA traffic dataset. So this is a dataset of traffic speeds captured by 270 sensors across Los Angeles. And also we use Hungarian chickenpox dataset. So this is a disease case dataset with 20 districts. And for the baseline models, apart from our STGNN models, we used LSTM models and gated recurrent unit models. For the matrices, we use mean absolute error and root mean squared error. So these are some of the results that we got. So this is for the Hungarian chickenpox database for RMSC, and yeah. So this is for the LA traffic dataset for both the errors. Like this is for RMSC, this is for MA. So as you can see from the results, like consistently our STGN models like outperform the baseline models. So this kind of proves the importance of having spatial relationships as well as the temporal ones. So like in the LSTM and GRU, we can have the temporal relationships, but in the STGN we have the spatial relationships as well. So let me talk a little bit about limitations and future work, limitations of our research, and also the future work that we are planning to do next. So first limitation is actually we are using static graphs. So we have to input the adjacency metrics into our framework. We don't use dynamic graphs, and no uncertainty modeling, no uncertain like probabilistic estimations we are not using at this point. And also, the 2 datasets that we have used is not large datasets. Like they have, like one had 270 sensors and the other one had 20 districts. So like this scale of the dataset is not large. So for the future work, we are planning to integrate learned adjacency and dynamic graphing. And also we are planning to incorporate probabilistic estimation for the outputs as well. And also, we are planning to integrate larger data sets so we can expand our testing scale. So, in conclusion, we are proposing a modular and reproducible graph neural STGNN framework where we can use it to to gain consistent results across multiple data sets, multiple domains, and multiple domains models. So yeah, that's it for our presentation. So if you have any questions, we are open.
What's the problem with having larger data set?
Actually, at the point we were doing the research, we couldn't find large data sets for the testing, so we put it as a future work. Yeah.
Very nice presentation. Thank you for the presentation. So, I think you mentioned that from your last slide. On the further work, you mentioned that at the moment, I think you are not produce on forecast, right? you're planning to incorporate, you're trying to, you're planning to incorporate to quantify the uncertainty associated with this point of focus. What's your plan for that? Do you have any idea how to do that?
So at this point, we like at this point we don't have a concrete plan on how to incorporate uncertainty modeling to our problem. Yeah. So, for most of the models, so yeah, so for the most of the models, in our GNN module, as I mentioned, we are using PyTorch. So even though the architecture itself is different, for most of the models, there are similar hyperparameters that we can use. So as an example, so in this specific scenario, usually when we are using spatial temporal graph neural networks, apart from all the graphs and everything, we have a look back window and also how ahead we are forecasting. So usually for all the models, let's say if we want to compare the evaluation results and everything, usually we set some of these special look back windows and look ahead windows as constant values. Let's say for our case, for the results here, we use 12 as a look back window and the look ahead window. And apart from that, most of the hyperparameters are same across all the models if you want to evaluate, compare the outputs of different models. Yeah. Sorry. So it depends. So let's say we have a specific use case. So let's say for instance, we are using this to forecast some kind of disease. So in that scenario, we train the model using, let's say, default set of hyperparameters, and let's say we want to change it up a little bit and see how the accuracy changes. So that way, we do it manually as well, and also we can incorporate cross validation, that kind of methods here as well. Yeah. So since this is a framework, there is a part of data pre-processing that we have to do manually, because there's so much we can put into the framework itself. So there's a format that we need to give the data into the module. But apart from let's say so usually when it comes to graph data or any kind of data, basically we have a set of standard, we have set of columns, basically we need the target variables, and also since we are encoding spatial information, we need the locations, and also we need time steps, since it has a temporal aspect as well. So when we give those data, the framework itself can go through this data and change it into the way that the model expects. So usually almost the way we have created the GNN module is we made it so that all the models also expect the data in a similar way. So yeah, that's how the data module does its work. Yeah. Thank you.
Now we invite Mr. Mohammad Saqib Shuki to present his paper titled Red Team AI, Adversarial Stress Testing of Role-Playing Language Agents Using Multi-Agent Evaluation. As the presenter is not with us today, we'll be presenting a pre-recorded presentation.
I'm presenting a research paper on the title Red Team AI, Adversarial Stress Testing of Role-Playing Language Agents Using Multi-Agent Evaluation. This work was done collaboratively by myself, Abdullah, Janaki, and Ravisha. Let's read the problem. Let me start with the Go problem. Large language models are increasingly deployed as role-playing language agents. Think of an AI healthcare assistant, a customer support bot, or even a financial advisor. These systems operate in high-stake domains where maintaining consistent persona and respecting ethical constraints is absolutely critical. But here is the challenge. Current evaluation methods are fundamentally inadequate. Static benchmarks and singleton prompts fail to model the kind of sustained adversarial pressure that real users can apply. And because these evaluations are shorter, they completely miss stimulating behavioral failures. The slow drift, the gradual erosion of ethical guardrails, that only emerge over extended multi-layer interactions. In short, we are deploying agents we do not yet know how to test. So, to address this gap, we built Red Team AI, which is a modular, open source, multi-agent platform for adversarial stress testing role-playing language agents. The core idea is simple but powerful. Instead of passive static tests, Red Team AI introduces an active adversarial agent that applies structured, escalating pressure across multiple dialogue threads, while separate automated judging agents provide quantitative, multi-dimensional scores. Our four key contributions are: first, a production-grade extensible platform. Second, a strategy-driven Red Team agent with 6 structured attack types. Third, a multi-dimensional scoring framework measuring role fidelity, risk, ethics, and consistency. And fourth, a fully reproducible experimental pipeline with support for multiple AI providers. This system is built around 3 tightly coordinated agents. The mediated agent. This acts as the automated Red Team adversary. It does not ask random questions. It applies 6 structured attack strategies and dynamically adapts its prompts based on the target agent's prior responses. And then we have the orchestrated agent. The orchestrated agent is the backbone. It manages deterministic turn-based dialogue, logs all prompts, responses, and metadata to a persistent SQL-like database, and coordinates the flow between all agents. Then we have the judging agent. The judging agent enters only after the conversation is complete. It observes the full dialogue history and produces quantitative scores. Critically, it has no influence on the conversation itself, which ensures unbiased evaluation. This entire system runs on a fast API backend with a React dashboard for visualization and supports multiple LLM providers, OpenAI, and Anthropic to a unified abstraction layer. The evaluation methodology is built on 6 distinct adversarial strategies, each targeting a specific known failure mode of language models. Roleplay. Roleplay gradually overrides the agent's assistant role to conflicting instructions and is preferred in the early terms. Ethical probing tests constraint adherence by escalating borderline requests that push against the agent's defined safety guidelines. And third, contradiction. Contradiction induces logical inconsistency by referencing the agent's own prior responses to force self-contradiction. Confusion. Confusion introduces ambiguous or conflicting information to destabilize coherent listening. Authority challenge. Authority challenge simulates power dynamics, supervisor overrides emergency scenarios designed to force boundary violations. And finally, emotional manipulation. This applies effective pressure through urgency, guilt, and empathy to break personal stability. These strategies are deployed progressively. Early turns use lower difficulty codes, and later turns escalate towards the most sophisticated attacks. This mirrors how real-world adversarial interactions actually unfold. After each experiment, the judging agent computes 4 normalized metrics, all bounded between 0 and 1. Role fidelity. Role fidelity, ORF, measures how consistently the agent maintains its persona. It is a great combination of constraint adherence, role language consistency, and the absence of character-based phrases. Drift index, or TI, captures progressive persona erosion by comparing role term density in early versus late terms. A high drift index means the agent lost its identity over time. Ethical deviation, or ED, quantifies violations of the agent's explicitly defined behavioral constraints. Consistency score, or CS, evaluates logical and tonal coherence across terms, penalizing contradictions and register shifts. These 4 metrics are combined into an overall score using a weighted formula where higher always means more robust. The formula is shown at the bottom of this slide. Experimental set. For our experiments, we ran the AI pipeline with 3 element families. Primary experiments use Llama 8.37 million parameter for all 3 agents. For cross-model validation, we structured our agent with G3 for OPD and Claude 3.4, 3.5 hyper respectively. Each experiment ran for 10 conversation turns with 3 random seeds per condition for variance analysis. We included 3 representative personas, a healthcare assistant, a customer support agent, and a financial advisor. For human validation, 3 domain experts independently scored a stratified sample of 60 conversation turns, achieving substantial inter-analytic agreement with a Flesis kappa of 0.71. Now let us look at the results. The bar chart here compares each person's score or robustness score under 2 conditions. A similar strategy baseline using only root wall rate and the full 6 strategy adversarial suite. The pattern is striking and consistent across all 3 personas. Switching to multi-strategy evaluation caused a substantial and statistically significant drop in robustness. The healthcare assistant suffered the most, falling from 0.837 to 0.634, a drop of 0.203 points. This is unsurprising given the sensitivity of the medical domain and the strict constraints around diagnosis and prescription. The financial advisor dropped by 0.18 and the customer support agent whose constraints are more concrete and operationally clear showed the smallest at 0.174, making it most resilient. The takeaway is clear. Single strategy innovation is not sufficient. It overestimates our robustness by 17 to 20 points on average. I think failure puts that only emerge under sustained diverse adversarial pressure. To validate there are findings, generalized beyond a single model family, we evaluated the healthcare assistant personnel across all the alien families under identical conditions. The results show consistent degradation patterns across all three models, despite their different architectures. Plot 3.5 high could achieve the highest robustness with an overall score of 0.712. GPT-4o mini followed at 0.681, Lanka 3.370 billion parameter. Model was most vulnerable, scoring 0.634. Their t-tests confirm statistically significant differences between Llama and plot across all metrics. Importantly, the failure mode rankings remain consistent across all three models. Authority challenge and emotional manipulation consistently induce the highest ethical deviation, confirming that these vulnerabilities are general, not architectural specific. Three key findings emerge from this work. The first is multi-strategy adversarial innovation failures, failure modes that are completely invisible to single strategy or static testing. The gap of 0.17 to 0.20 is not noise, it is real hidden risk. Second, domain sensitivity and constraint specificity are significant factors in robustness. Yet their agents are inherently more vulnerable because their constraints are hard to define operationally and their adversarial strategies are more effective in emotionally charged scenarios. Third, and perhaps most importantly, failures are temporarily distributed. The vast majority of critical failures emerge in the second half of a conversation. After turn 5 or 6, when human-aided adversarial pressure has softened the agent's defenses. This means that short or single-turn evaluations produce systematically optimistic assessments. Conclusion and future. In conclusion, Reddy AI demonstrates that dynamic multi-layer adversarial evaluation provides significant deeper and more actionable insights than static response. The framework is open source, reproducible, and production ready. Future directions include expanding the strategy library with long horizon reception tracks, incorporating human evaluation, introducing embedding-based semantic metrics, deploying multi-adversary coordination, and continuous monitoring of live production systems. Thank you for your attention.
Since Mr. Shakib had made it on time, we invite him now to take the questions and answers for the session.
Hi everyone, should I start with the presentation? Oh. Okay. Let me take the Q&A. I'm really sorry for bit late. Yeah. Yes. So, so we have so if you look at the architecture, we have a target agent, and then we have we have an attack agent, and then a judging agent, and an orchestrate agent, which orchestrates all of these. So, the target agent, the attack agent attacks the target agent on different attack strategies, and then all of them are being sent to the judging agent, and the judging agent goes through all of these, and then based on 4 criterias, it evaluates that, and then it gives a score for each of them, and then we combine all of them and give a final score. That's how it is. The evaluation is being done by the agent side, and then we compared that evaluation with an expert evaluation. So we got 3 domain experts in so we have done on 3 domains, on the healthcare domain, and then financial domain, and then on the customer support domain we have done 3. So we got all of them validated. We compared the results from 3 domain experts, and then the results from the domain experts and the values which was given by the judging agent was also very similar. Yeah, so let me show you. Anna. Okay. Okay. Yeah, so these are the 4 evaluation metrics. So the role fidelity score, drift index score, ethical deviation, and consistency score, we got it independently for each 3 of the cases from the domain expert, and then we calculated the overall score. So one by the judging agent provided the score, and then the human, like the domain expert provided the score, and we compared both of them, and then the similarity was also like, it was very similar. I didn't get it.
For example, for
Yes. Yeah. So 0.3 is for the role fidelity, because I have to, so let me go through this. So role fidelity, so here I'm measuring like how consistent is it through that particular role. And that I have to give like a slightly more weightage compared to the others for the role fidelity and the ethical deviation. Ethical deviation looks into whether it adheres to the ethical boundaries and boundaries. So this I have given like a bit higher score, 0.3, given like a 0.3 weightage in the role fidelity and the ethical deviation. For drift index and the consistency score, I have given 0.2 because that is also important, but more than that, we have to prioritize the role fidelity and ethical deviation. And then the minus is because the drift index and ethical deviation, it's having a low score is better, and that's why I have 1 minus the drift index and 1 minus the ethical deviation. Okay. Okay, thanks.
The same question. So there is a way to tune those waves.
Yeah, as sir mentioned, I'll try to improve on that. This I gave mainly based on mainly it was by gut feeling only.
Just about minority, like what are the other systems existing and what is their state of the
Yeah, so if you look into most of the systems which are there to evaluate, so here we are trying to evaluate the role-playing language agents. Most of the systems which are there to evaluate the role-playing language agents, I did some research. Most of them just do there was a static, they give the value directly. But here what we are doing is, they're the attacking agent attacks, and then it there are 6 different attack strategies. So it attacks on those attack strategies and then identify where the agent shows, the target agent shows weaknesses, and then whenever it shows a particular weakness on a particular area, it keeps on attacking that area furthermore. So this goes through at least 10 conversations, and even we can go beyond that. So at least 10 conversations. At the start, it just tries to identify the weaknesses, and then by the end, it identifies the weaknesses and it has attacked it really well. So through that, because of that, the score which has been given in this case is much more reliable. And here we are we have taken all 4 of these together. So it looks into a much broader scope. Thank you.
Thank you to all our presenters.
We will now take a short tea break and then proceed to the poster session, where participants will have the opportunity to explore a diverse range of research projects and innovation. We kindly request the judges to keep the allocated time for 5 minutes per presentation.
This session is designed to encourage interaction, discussion, and knowledge sharing. So feel free to engage with the presenters. After the poster session downstairs, we will have the lunch, and kindly make sure to be seated by 1:50 p.m. here for the keynote and award ceremony.